Given that we are talking about clustering, let's talk a bit more about it. And as of now, you see, clustering is one of our concept that makes our real world networks not random networks. So you saw that when we created random networks, we didn't find any clustering there. It is one of those central concepts which makes real world networks different. Take a look at this. Clustering is also sort of an ambiguous idea in this field. I say ambiguous because it has many definitions, many forms. So I'm just providing you some clear technical jargons here, more useful from the perspective of exams. We'll look at three ways in which clustering comes. So this is the first way. This we have discussed multiple times in the class, which is at the individual levels of a node. If you're talking about one particular node, can you tell me how well knit is the network of this node? So if you look at the friends of this yellow node over here, how well knit are the friends of this yellow node? We call that clustering coefficient. You look at how many friendship ties are there between your friends. In this case, there are 4 existing links between the neighbors. And then you see what is the total possible number of links, that is 6. So if you look at the friends of this yellow node over here, there are 6 possible links between them because there are four friends. 4 choose 2 is 6. And out of those 6, only 4 are there. So clustering coefficient of yellow node here is 4 by 6. That's one way to formulate clustering. We looked at yet other way in the last hands-on, which was transitivity. And there we were more concerned about, if you look at all the triads in a network, what fraction of these triads are closed? If we have Amar, Akbar, Anthony, Amar is a friend with Akbar and Anthony. Are Anthony and Akbar friends with each other or not? And if it's a real world network, it should happen like that. If you are good friends with two people, better they be friends with each other. How do we capture it? With the transitivity. Let me actually show you some of the codes which have been submitted by you only, which provide you a better idea of this. What we were interested last time was, if you model these random networks, you don't find clustering there. This is Ayushi's code that I have picked. I'll show you only the major points in this code, the things that I want to talk about. Here is where she creates a random network. I hope this is clear to all of you. We had 121 nodes in this graph. So we just added 121 nodes, which you can see here. And now we wanted to add, let's say 188 edges here. So what we have done, we randomly picked pairs of nodes and we added 188 times. And you got your random graph. If you look at the properties of this random graph here, density of this graph is very low as expected. Let's say 2%. Average path length is also low, 4. That means it's a small world. But if you look at the transitivity of this network, what fraction of triads are closed, how many triangles you see, that fraction is very less. It is only close to 2%. If you remember the friendship network that we are using in our course as a benchmark, our friendship network had a 60% clustering, and this one over here has only 2%. So what Ayushi did here is, Ayushi, you can comment on this video if you think what I'm saying here is incorrect. I didn't understand it properly. So what she is saying is, once you have created these random links, maybe God hasn't done his work properly, he sprinkled some random ties, but once that is done, people will start forming triangles. First you make this random network and then just throw some triangles at this network. How do you do that? You randomly choose some nodes and this time choose 3 instead of 2. Choose 3 random nodes, make a triangle between them. Again choose 3 random nodes, make a triangle between them. That's how we are incorporating triangles in this network. Ayushi incorporated 100 such triangles. That increases the clustering of this network to 51%. A quick idea, what is done here is you first create a random network and then you throw in some triangles to increase the transitivity. What Lohit did, what he was explaining last time, is exact opposite of this. Not an exact opposite, but quite opposite of this. So this is Lohit's code, which is sent to me on Discord. He is doing the opposite thing than what Ayushi is doing. So instead of creating a random network and then throwing triangles at it, first you create a lot of triangles and then you add some random edges to it. What is also interesting is you see the way he is adding these triangles here. He is now not picking some random edges, random nodes to create triangles. He is using the nodes which are close to each other. So basically nodes 1, 2, 3 will make a triangle. Maybe node 2, 3, 4 will make a triangle. So what he's saying that people make these triangles, but they make these triangles with the people who are close to them. Again, these triangles are not being formed across continents. You have clustering, but you see this clustering is also local. Your triangles are also local. So we will talk more about it. The overall idea here is, the main idea of this code here is, you first create a whole lot of triangles and then you add some edges, random edges on top of that. And I think Keshav also had a similar code. So this code, it comes very close to one of the standard models that we will be talking about. After these two codes, these codes increase transitivity in your networks. I think Lohit also had close to 60% transitivity. Now there is one more way to look at clustering. So one way was clustering coefficient. Second way is this kind of transitivity here. What fraction of triads are closed? Here is the third way. You see communities in the network. It's most easy. It's the most interesting and the easier one to see also. Overall, your network is sparse, but then you find that this network is dense at few places. So, I'm sorry. Dense at few places, right? So how do you create such kind of communities in networks? And then some of you have written codes explicitly to create such kind of communities. I'm not going into the codes, but let me show you some of the end products here. This is one graph which was submitted by Srinath and team. Do you see here communities of people, and then these communities are connected by these big paths. So you have this sparse graph which has these dense communities. So community is the term we are going to use for this. And this is one more effort by Taruni and team, a similar looking network. I think Amruta has also submitted a similar code. So these are different ways in which you can achieve clustering in your networks. And this particular way of creating communities, it also comes close to standard models in this area. I'm actually glad that some of the codes that all of you have submitted, they come really close to the standard models. And I was just thinking that if you guys were born 10, 20 years ago, one of you might have proposed the standard models that we are going to study next in the course. Many of these models came only around the year 2000, since the field is new. So yes, we'll be talking about that. So that is about clustering. So right now we are at a stage, we just saw that random networks are not a real representation for real world networks, because real world networks has clustering, one of the most important properties. We'll be looking at more properties of real world networks. What I'll be doing next is I'll be discussing some of the standard models, and I'm sure you won't find them difficult to understand because we've already come up with similar models.